right, thank you, Richard, for the introduction. Thank you, everybody, for being here this morning. So indeed, I'm moving from MIT to ENSAE, but I don't have the logo of ENSAE yet, so I had to put MIT. But yes, in I guess less than 10 days, I'm officially French again.
You'd never get
So I'm going to talk to you about some notion that has been introduced by Tukey in the 70s, and that's called the Tukey half-space depth. And in particular, I'm going to, I'm studying the contours of the Tukey depth for some distributions, and the convergence of the contours of the empirical Tukey depth given i.i.d samples from some distribution. So just to start, to give you some maybe some motivation that is also related to what I did previously during my PhD, I'll talk to you about random polytopes for a minute. So imagine you have n points, n i.i.d points in R to the d, x1, x2, xn, and you assume, for example, that they're uniformly distributed in some convex sets. And you would like, just given those points, you would like to estimate the support of the distribution of the xi's. So a very natural estimator that is also provably optimal in some sense, in a minimax sense, is to take the convex hull of those points. So this is a random polytope. So here in 2D, it's a random polygon. But in general, in d dimensions, it will be a random polytope. And it has been studied a lot since the seminal work of Renier and Soulanke in the 60s, where they studied this object in dimension 2, when d is equal to 2. And they studied, for example, the expected value of the area of this polygon, given that the points are i.i.d. Uniformly distributed in some convex sets, for example, a triangle, like in my picture. Then Efron studied some more properties, and also he extended some results in dimension 3, and then many people started studying this random object. So, and I studied, during my PhD, I studied this random object as an estimator, and I studied optimality in particular of this estimator for when you want to recover the support of a uniform distribution. And I have some results also when the distribution is not uniform, but okay, this is not relevant here. So, in general, this object, as I said, is useful if you want to do some estimation, so support estimation, but it's also relevant if you want to do some clustering. For example, if you imagine that you have many groups and you may want to compute some local convex hulls, so meaning some local random polytopes that will give you the clusters of your data, for example. Or you could think of, I mean, support estimation has also been studied in the 80s for detection of abnormal behaviors. So for example, imagine now, so you have your n data points, and I give you a new data point, and you want to decide whether it's abnormal or not. So what you can do is, well, check if this new data point belongs to the convex hull of your previous data points. This is something that you can do. And speaking of which, actually, this estimator is actually absolutely not robust to outliers, so to abnormal new data. So look at this. Imagine that you have actually one of your data points that for some reason is completely off, and that comes from some contamination. Then, of course, this object, this random polytope, is very bad. It becomes an extremely bad estimator of the support of the distribution. So actually, the idea of this talk is to fix. Yes, it's to fix the signal. Yeah. Okay. So the idea of this talk is to try to fix this. So by considering some different version of this random polytope. So, okay, you may be familiar with the with many possible definitions of the convex hull of endpoints. So when you have endpoints, the convex hull, so it's the smallest convex set that encloses all the points that you have. But you can also show that this is the intersection of all closed half spaces that contain endpoints. If you have endpoints in your sample, you look at all the half spaces that contain endpoints, and you take the intersection of all of them. But now, if you want to do something a little more robust, you could take the intersection of all half spaces that contain n-1 point. And then this will give you the red picture. So that will already be robust to some outliers. And if you want to do something a little more robust, you can compute the smallest, the intersection of all half spaces that contain n-4 points, for example. But or n-2 points, n-3 points, or in general n-k points for a fixed k. And that is going to be called the k-hole of your sample. So the convex hole is a particular case, it's the zero hole. But you could think of computing the k-hole that will be more robust, and of course you would not want to take k that is too large, otherwise the set will shrink. And it will become too far away from the actual support that you would like to estimate. So this could be one possible way of fixing the fact that the convex hull is not robust to outliers. And in this talk, actually, I'm going to study the k-holes, but I will study k-holes for k that is linear in n. So k that is not too small. So I'm actually, in this talk, I'm not going to talk about k-holes for k that is equal to 1 or 2 or too small. I will focus on k-holes when k is going to be sufficiently large, actually linear in n.
So computationally here, I can see that computing the one hull is not too bad, right? You could just need to think about the points on the boundary of the convex hull and think about leaving each one of those out.
So correct, in 2D, computing the one hull, even computing the k-hole in general in 2D, you can do it in n squared step, order of n squared step. In 3D, there is no known algorithm to compute exactly the k-hole.
How does it work for k larger than 1? I thought this is your question.
I was working up towards
Oh, how does it work for k larger than 1? Yeah, there are some quite complicated algorithms actually, but that are indeed, so they are not based so they are not first computing the convex hull and then fixing it. They are actually completely independent of the computation of the convex hull. One thing that is that I find very interesting and that actually makes the problem of computing those sets hard is that, as you can see, so let's go back to this picture, the vertices of the convex hull are all data points. Each vertex is actually part of the data. But when you look at k-holes, this is no longer true. So you see, for example, here you have one vertex, and here as well, that are not that do not belong to the data. And this actually makes the problem a little hard. Also, there are some super nice results, I think, concerning the expected number of vertices of the convex hull. And you can prove very nice formulas, very neat formulas. So one is due to Efron in actually 1965. I'm not going to talk about it, but if you want to look at this paper, it's actually very nice. But I have absolutely no idea of how to understand the expected number of vertices of the k-hole. When you have n i.i.d points that whose distribution is known, let's say uniform in the Euclidean ball, for example, how to understand the expected number of vertices of the k-hole, of the one hole, if you want. So if you look at the zero hole, even the expected number of k faces, so k faces meaning, so the convex hole is a polytope, so it has some vertices, it has some edges, it has some faces of dimension 2, 3, etc. So for any fixed k, you can actually understand the expected number of faces of this random polytope of dimension k. This is very well understood, but when you look at those holes, there is nothing. There's absolutely nothing, and I really have no idea how to approach the problem. But this is not actually, this is not part of this talk, anyways. So what I want to talk about is Tukey depth, and let me just remind some extremely basic definitions in dimension 1. So here I draw some i.i.d. Gaussian, standard Gaussian points, so 30 of them, in dimension 1. let's try to understand the Tukey depth in dimension 1. So, okay, in dimension 1, you can define the CDF, the empirical CDF. So the empirical CDF just counts the number of points that are less or equal to some threshold. You can define the empirical quantiles. And by the way, in this talk, each time I talk about quantiles, I'm going to talk about upper quantiles, because you know quantiles are not always uniquely defined. I'm always talking about the upper quantile. So the upper quantiles, the empirical upper quantiles are defined by such a formula. So for example, if you look at the upper, the empirical 90% quantile, so for alpha equal to 0.1, this gives you the last decile. So here it's these red points on the right side. And you even have, you can actually write the empirical quantiles in terms of the order statistics in dimension 1. So, okay, I don't actually care about this formula here. Okay, so this this red point is the last decile. So you want to say that this point is in some sense is extreme. It's very far away from the center of the distribution, right? It's almost at the edge of your cloud of points here. But you also want to say the same on the other side of the distribution, on the left side of the distribution. So that now comes my time to pretend that I'm a fancy PowerPoint user. And you want to do the same once you flipped the picture. So once you flip the picture, then this point, the third, when you come from the right, will become also red. And then you want to say that, okay, again, you want to say that all the points that are between those red points are more central or less extreme, or actually they are deeper in your cloud of points, deeper than those two left and right last deciles. So, okay, this drives the idea of the definition of the Tukey depth. So let me give the general definition of the Tukey depth and then go back to the one-dimensional case to make sure that we're all on the same page. So in general, you have endpoints, x1, x2, xn. So in my case, I will assume later that they are i.i.d with some probability of mu. But you have those endpoints, and you can define the Tukey depth of a given point x in the space in R to the d. So take a given point, that not necessarily a point of your sample, just take a point x in the space, and then look at all half spaces, closed half spaces that contain x. And among all those half spaces, look at the one, or one of them, that contains as few data points as possible. And this number of points contained in this optimal closed half space, if you divide it by n, this will give you the definition of the Tukey depth. So the Tukey depth at a given point in the space is the smallest proportion of data points included in some half space that contains x. And so you see that you can rewrite it as the smallest value of the empirical probability mass contents of some half space that contains x. So you can write it as the infimum of mu n, which is the empirical distribution associated with your sample, of h, for h that is closed half space containing x. And then you can define the same at the population level. So you can also define for each small x, for each point in the space, you can define the population version of the Tukey depth as the smallest value of mu of h for h ranging in the class of all the closed half spaces that contain x. So let's see in this one-dimensional example. So look at any of those two red points. So in dimension 1, half spaces, or again, when I say half space, I mean closed half space. But so in dimension 1, a half space is just a half line. So look, for example, the red point that is to the right. So look at all possible half spaces that contain these points. Well, it's just the half lines that are unbounded to the right and that contain this red point, or the ones that are unbounded to the left. So now, if you want to take one such half space that contains these points and that has minimum, that contains the smallest amount of data points, well, it's going to be the half space that starts at the red point and then goes all the way to the right. And it will contain exactly 3 sample points. So the Tukey depth associated to this red points is going to be 3 divided by n, which here is 3 divided by 30, which is 10%. And same for the leftmost red point. Its Tukey depth, empirical Tukey depth, is also going to be 10%. And all the points that are in between will have a Tukey depth at least 10%. So they will be deeper. Their depth, their Tukey depth, is going to be at least 10%. So, okay, here now comes also the time of using this very fancy system. So if you have if mu is, now let's just make sure that we understand the definition. So if mu is the d-dimensional Gaussian distribution with mean theta, given theta, and a covariance matrix identity, then let's put theta here and x here. So at a given point of the space, I want to compute its Tukey depth. So it's not very hard to see that the half space that contains x and that has the smallest probability content is this one. It's this one, and then the Tukey depth of x relative to this probability measure will be the probability content of this space, which is exactly, so here, this distance is just the Euclidean norm between of x minus theta, and so you will have 1 minus the probability content of this half space is just the probability content of once you project the Gaussian distribution in the direction corresponding to x minus theta. You just look at the probability content of this one-dimensional relative to this one-dimensional Gaussian distribution, which is n projection of theta. I mean n projection of theta and 1. That is past Euclidean norm of x minus theta. So I think it's quite clear that this gives you this. So now, if more generally, if mu is Gaussian with d-dimensional Gaussian with parameter theta and some covariance matrix sigma, then you can draw the same picture. But now you have to account for the fact that you don't have identity as covariance matrix. So what you can do is draw the level sets of the densities, so that are ellipsoids that correspond to sigma, and look at the direction and orthogonal to the ellipsoid that touches the first ellipsoid that touches x, and this will be the half space that has the smallest probability mass and that contains x, and d mu is going to be this. You can show it pretty easily. Yes, absolutely, it's correct.
Why is one-dimensional? It's the CDF at a point.
Yeah, so because you project, actually, when you want to compute the probability mass of a half space, you have to project your measure, and then you have to project your measure in the direction that is orthogonal to the boundary of this half space. And then it's going to be the probability content for the one-dimensional projection of a half line. Yeah, there should be a square root indeed. Right, so now, okay, I hope we all understand the definition of the Tukey depth. So the Tukey depth is a function that maps any point in the Euclidean space to some number between 0 and 1. And you can now think of the contours or the level sets of this function. So again, if you have your data, so you have x1, x2, xn, then if you look at the level sets of the empirical Tukey depth, that will give you exactly the k-holes. You can see, I mean, you can see that if you scratch your head for 1 minute, maybe. Okay, but so in general, I will define so G, the level set for at the population level. So when alpha is some fixed number between 0 and 1, strictly between 0 and 1, then G will be the level set at the population level. So it will be the set of all points that are deep enough, so whose depth, Tukey depth, is at least alpha. And yes?
One quick question. If x is equal to theta, it should be like 1/2, no?
Yes.
Gives you 1.
Yes, it will be 1/2.
Oh, okay.
Yes.
So I don't plug in. Oh, I see it. That's right. That's right. 1 minus 1.
Yes.
That's right.
So okay, and the level set at the empirical for the empirical measure is going to be the set of all points x for which the n, so the empirical Tukey depth, is at least alpha. And again, so as I was saying, you can show that this level set is the same as the k-hole for k that is basically of order n alpha. So this is exactly what I was saying. I will only focus on the k-holes where k is linear in n. So k is of order n alpha for alpha that is strictly between 0 and 1. Alpha is a fixed number between 0 and 1. And what you can show is that those two level sets, G and Gn, are always compact and convex sets. So what I want to understand here is how Gn hat, this empirical level set, converges or concentrates in some sense around G. And I'm going to use a lot of tools from, mostly from convex geometry. Okay, but one question actually related to what you just asked, one very natural question that you may ask is, okay, so for example in this picture, I see that, so I drew the level sets of the empirical Tukey depth, which are the k-holes, so they shrink, but at some point it becomes empty. So for which are the alphas that are reasonable to look at? Because maybe if I take alpha that is greater than 1/2, there is quite a chance that my sets are empty. But, okay, for example, in dimension 1, it's pretty clear that when alpha is equal to 1/2, the set is non-empty, because at least the median of your distribution is in the set. And in dimension D, so look at the second line here, I mean this here, you can show that this extends in dimension D. If you look at alpha that is that can be all the way, I mean, as large as 1/d+1, then the corresponding set is going to be non-empty. But if you take alpha to be half, or actually if you take alpha even to be a little more than half, the set will either be empty or it's going to be a singleton. And in that case, it will be a singleton that contains the point mass of the probability distribution. So in particular, if the probability distribution has no point mass, then the set will be empty whenever you take alpha that is strictly larger than half. So, and also one nice thing is that if mu, the distribution, is log concave, then it's a pretty standard result that says that whenever you take, well actually, okay, the most simple way of stating this is that when you have a log concave distribution with, I mean, okay, let's say that 0 is the centroid, then the CDF at 0 is always at least 1/e. Always. So, and that means, as a simple consequence of that, whenever you have a log concave distribution in RD, any half space that contains the centroid, so the mean of that distribution, has probability content at least 1/e. So it means that if you take alpha, anything that is less or equal to 1/e, if you know that mu is log concave, then the set G is going to be non-empty. Which is nice because this, the second line here, to say that G is non-empty, that, I mean the line, the property that ensures that G is non-empty as soon as alpha is less or equal to 1 over t plus 1, is not very, very useful because 1 over t plus 1 is small if d is quite large. So, but at least we know that the set is going to be non-empty for large alphas as long as we know that, for example, mu is log concave. All right, so what are they useful for? So as I explained to you, there are those two depth level sets. There if you see them as k-holes, they can be useful for robust estimation of the supports. In general, they are, so Tukey in 75, it was at the International Congress of Mathematics that he actually gave a talk about Tukey depth, and he was explaining that this is a very nice tool to for this data visualization and data description. So yeah, then some work has been done in descriptive statistics in more generally, and what we'll understand in the next couple of slides is that those level sets are sort of an extension of the notion of quantiles, but in d dimensions. So those are, the way I call them, at least in the paper, is multivariate quantile sets. So, and in that sense, they're actually useful just as quantiles in one dimension are very much used, I guess, in high school, when you teach statistics in high school. Not you, but other people. I mean, students learn about things like median, deciles, and box plots. Those in French we call them moustache plots because they look like moustache.
Box and whisker plots.
So, yeah. Oh yeah, yes. So all right, they can be used for that, and okay, I talked about robust inference. They can be used for classification, for the same idea as I was telling you when you want to do clustering, for example, but robust clustering, instead of looking at local convex hole, you may want to look at local k-holes. Which is actually, I'll be honest with you, which is a very bad idea because we don't know how to compute the k-holes, right? But I will talk about that a little later as well. So, okay, to continue on what I was saying about this idea that those sets extend the idea of quantiles, but in higher, I mean, in the multivariate case. Let me introduce those two pieces of notation. So, okay, you have your distribution mu, and you have your the empirical distribution mu n, and now let's look at the projections of those two distributions along any possible direction of the unit sphere. So for any u in the unit sphere, I will look at well, I will look at the distribution of the inner product between u and x1, where x1 has distribution mu. So this is exactly to say that I'm looking at the projection of mu along the direction u. So this gives me a one-dimensional distribution, and I denote by qu the 1 minus alpha upper quantile of that distribution. And I do the same for the empirical distribution of the data. So I project all my data onto one line corresponding to the direction u, and I will do that for all u. And I define qu hat to be the 1 minus alpha empirical quantile associated with this projected sample. And what you can show is that you have these very nice polyhedral representations of g and g hat, but say that g is the set of all x's such that when you project x in the direction u, you get something, a projection that is less or equal to qu. So you're below the 1 minus alpha quantile in the direction u, and same for the empirical version. So you have those very nice polyhedral representations of g and g hat. When I say polyhedral, I mean that, as I told you, g and g hat are convex sets, compact and convex sets. And here I'm saying that g, for example, can be obtained as by looking at all those linear constraints. So in each direction, I draw a hyperplane corresponding to this linear constraint, and I do it in all directions, and I get something like this. So it's a little misleading when I say polyhedral representation, because G is not a polyhedra. G is not a polytope in general, because you have infinitely many constraints. However, G hat, actually, many of those constraints in G hat are not active, are not necessary. So actually only finitely many of them will matter, and G hat will be a polytope. So you could actually show that G hat is always a polytope. All right, so as I promised, I want to understand now how G hat and how G hat behaves with respect to G. So how G hat approaches G. So for that I need to introduce the notion of metric between sets, between convex sets. So okay, first let me cite maybe a few papers. So I want to understand how G hat approaches G, so how G hat concentrates around G in some sense. And some people have studied this problem before. So, okay, first of all, I'm looking at the Tukey depth. So you may actually have heard other notions of depth, of statistical depth. There is the simplicial depth. There are other notions of depth, and actually there are a few very nice papers. So Zerfling has a paper where he introduces the notion of depth. So what a function is called a depth if and only if it satisfies a few properties. And then for any function that is a depth, and the particular case is Tukey half-space depth, they show that if you look at the empirical contours, they're getting close in some sense, in some quite weak sense, to the true contours of the population depth function. But since they are very general, so in that paper, for example, in 2000, they are very general, and they only achieve consistency only in some sense because they don't consider one specific depth. And in general, the results that I'm going to present are not necessarily true for any depth function. So consistency also had been studied a little earlier than that, and some results that are a little more, a little stronger than just consistency were also proven by Kim in 2000, but under some very specific assumptions. For example, mu had to be unimodal, and here we'll see that I mean, the assumptions that I'm going to make on mu are going to be extremely general. Okay, not extremely general. They are going to be general, and I will also have very explicit constants and very explicit bounds, unlike what was done in these papers. Okay, so as I was saying, we have to understand what it is for G hat to become closer and closer to G. So I have to talk about some metrics in distance between sets. So a very natural distance is the host of distance between two convex sets. So, okay, to understand the host of distance, you have G1 and G2. Take a point in G1 and look at the point from G2 that is the farthest away from X. So take X in G1 and look at which point is the farthest away in G2. And then look at the supremum over all points in all X in G1. And do the same for by exchanging G2 and G1. And take the maximum of those two values that you get, and this is the host of distance. So I would agree that this, I would agree with all of you, I would be frowning as well, and I would be like, yeah, I don't really understand this definition. So let me give you maybe a much nicer definition, I think.
But it's, you look at the closest point to G2, not the furthest point to G2.
Sorry, the closest point. Yeah, the closest point. Yeah, of course, the closest point. Otherwise, it becomes it's not a distance anymore. Yeah, for any x. Okay, yeah, my mistake. Oh, this is why everyone was frowning. So for any x in G1, you look at the closest point in G2 to x, and then you look at the supremum, the maximum distance for all x in G1, and you do the same for G2. But okay, still I will give you a better definition. Okay, so you have G2 and G1. And a very nice way of looking at this host of distance is the following. How much do you need to add to G1 in order to completely cover G2? So when I say to add something to G1, I mean the following. You can add some epsilon layer to G1, meaning that you just increase G1 by including to G1 all points of the space that are at a distance, that are within a distance epsilon of G1. So this enlarges a little bit G1. And how much do you have to add to G1 in order to completely cover G2? And then how much do you have to add to G2 in order to completely cover G1? And the maximum of those two answers is going to be the host of distance between G1 and G2. I think this is a nicer, maybe more intuitive way of seeing the host of distance. But I actually have another way of seeing the host of distance that is maybe much less intuitive, but that is going to be very useful here. So for that, let me introduce or maybe remind the definition of the support function of a convex set. So, okay, actually, I need to board again. And eraser. You have in RD, you have a convex body, a convex set, G, and so the origin is somewhere, let's say here. And now you look at some direction U, for example, so you take a unit vector U, and you look at, so G will have two supporting hyperplanes that are orthogonal to U. So this one, and this one. Those are the two hyperplanes that are supporting hyperplanes to G that are orthogonal to U. And you look at the last one. When you go from the origin in the direction U, you look at the last one, which is this one. And this signed distance will be called the support function of G in the direction U. So just to make sure, if I take this vector now, this unit vector V, which is in my picture the opposite of U, then the second hyperplane, the second supporting hyperplane, will be the left one here, because now I go in the direction of V. So now this is going to give you the support function, but it will be negative here because it's a sign. You look at the signed distance. So the signed distance when you basically project everything in the direction U. Or in the direction of V, I should say. So the formal definition of the support function is this. So the support function for any vector U, you look at the dot product between U and any point in G, any point G, x in G, and you will take the maximum value of this. And this defines the support function. So this is exactly what I wrote, what I drew on the board. And the nice characterization of the host of distance between any two compact and convex sets, G1 and G2, is that their host of distance is given by the L infinity distance between the two support functions as functions on the unit sphere. And this characterization is going to be very useful for us. So basically now I'm just going to look at the support functions of G hat and G, and I will look at the distance between those support functions, the L infinity distance of those between those two support functions on the unit sphere, and that will give me a way of measuring how close those two sets are. So, okay, recall that we have these very nice polyhedral representations of G and G hat. So you remember in terms of the projected quantiles, of those one-dimensional quantiles. And so in particular, if you look at the support function of G, so fix the direction U, it is clear from this polyhedral representation that u dot x cannot be larger than qu, right? But just from the definition from this polyhedral representation. So the support function at any u is going to be less or equal to q sub u. So let me let me say the following. Actually, let me draw another picture. You have G, your set G, can be defined in terms of those linear constraints. So it's exactly the same picture as I drew here. So let me. So here I drew a very, very nice picture that is completely unrealistic. So I drew this picture where basically in the direction u, if I take this direction u, this half space, I mean this hyperplane here, give me the linear constraints associated with u, right? And on my picture it looks like, well, okay, perfect. So let's even make the picture even more outrageous. It looks like, oh, that's perfect in that direction. Well, if I look at the support function, well, clearly this linear constraint gives me a supporting hyperplane of my set G. So clearly, in that direction, Hg should be equal to Qu. Right? It's quite clear because this hyperplane is at a distance Qu to the origin. This is how it is defined because this hyperplane is given by this. It is from the linear constraint that I have in my sets, and well, the support function is the distance from the origin to this hyperplane. But in practice, it's completely wrong because the picture is not as nice as this, because I may actually have, for example, imagine in this direction. So imagine the origin is here. If I look in this direction, so in neighboring directions, for example, here I have this linear constraint. Here I have this linear constraint. But maybe in that direction, for some reason, the linear constraint was here. And the linear constraint may actually never be attained in my sets. So this gives me, in that direction u, it gives me the linear constraint, but maybe it's not active at all. Maybe the support function here is going to be given by this hyperplane, not by this one. So in that case, I will have that the support function is strictly less than Qu, which is a little sad. I mean, it's sad. Math would be a little boring otherwise. But it's a little sad because, look, if it was the case that the support function of G was given by the Q's and the support function of G hat was given by the Q hats, then, well, I would use, I would just say that the Q hats concentrate around the Q's uniformly. That would be quite simple to show by some empirical process theory. And then that would be it. I would have some bound, some stochastic bound on the L infinity distance between the Q's and the Q hats, and hence between the support function of G and the support function of G hat. But this is not the case because the support functions are not actually given by those Q and Q hats. So I have to work a little harder. Okay, so actually yes, you can show the following. So imagine you have some family T sub u indexed by vectors in the by vectors in the space that are positively homogeneous, meaning that T of lambda u is equal to lambda Tu for all positive lambda. Meaning that I'm actually defining, I just need to define Tu on the sphere and then extend it to the space by positive homogeneity. So which is exactly what I have with Qu, for example. I have Qu that was defined for u only unit vectors on the sphere, but I can extend it by positive homogeneity. So, okay. And look at the set K given by those infinitely many linear constraints that are u.x less or equal to tu for all u in the unit sphere. Then the three following propositions are equivalent. All the linear constraints that are given in K are active, which is not the case in the red, for the red hyperplane that I had drawn over there. So all the linear constraints are active, if and only if the support function of K is actually given by T, if and only if T is subadditive, meaning that meaning that it's convex actually. T has to be convex, meaning that T sub u plus v is less or equal to Tu plus Tv for all u and v. And since it's also positively homogeneous, it exactly means that T has to be convex. So if I go back to G, well, that would mean that for G to be nice, for everything to be nice, I would need the QUs to be subadditive. The quantile function QU should be subadditive. But in general, let me ask you the following questions. For which distributions are the QU subadditive? That I don't know. And actually another question that may interest Richard, for example, and many other people. If mu is log concave, is it true that QU is subadditive? So, for example, you can, I will let you do the computation, but you can show that you can compute QU for Gaussian distributions. If you have Gaussian distributions with any covariance matrix, you can show that QU is subadditive. So sometimes QU is subadditive. But my hunch is that if mu is log concave, then QU is subadditive, but I don't know how to prove it. Okay, but I will not assume that QU is subadditive. I will not make such an assumption for now, because I still want to be very general. So, okay, let's first bound. Let's first do as if everything was fine, and let's see what happens after that. So let's bound this supremum of the distances between the empirical quantiles and the quantiles. So this is not very complicated. You can use some empirical process theory. Maybe I will not go over this. But of course, if you want to control uniformly on the unit sphere the error of Q hat, of QU hat, of course, you need at least to be able to control it pointwise. So you need to make some assumptions about mu. So for example, mu, when you project mu onto any direction unit vector u, so if I denote by f sub u the corresponding CDF, so it's the CDF of the projected distribution, then I will assume that f sub u is continuous in a small interval around QU. That's quite reasonable. And I will also assume that f sub u, this CDF is not too flat. Because if it's too flat, then there is no way for me to estimate the quantiles. If it grows too slowly around QU, then I will not be able to estimate QU very well using the empirical quantile. So I assume that the CDF of the projections uniformly for all projections. So I use the same constants. You see epsilon and capital L. I will assume that the CDF of those projections, they grow sufficiently, at least linearly. So that is a very reasonable assumption, I think, just to ensure that I can estimate at the speed 1 over square root of n, I can estimate the quantiles using the empirical quantiles. So it's the same as to say that locally I have a density, and the density is bounded away from 0. Okay, so then you can control. You use some basic tools from empirical process theory, and you can control this the probability that the supremum of this difference between q hat and q is greater than some z. But you can control it only for z that doesn't take you beyond this epsilon away from those quantiles qu. Okay, so that part is actually pretty easy. And the second part is actually the main difficulty that I summarize only in one slide, but believe me, it's a few pages. But okay, I will also assume that G, the true set, the level set at the population level, contains a small ball and is included in a large ball. So I'm assuming that for some center A, you can actually find some small ball with some small radius r included in G, and G is included in some ball. So the fact that it's included in some ball, that's clear because G is always compact. But I want something uniform because actually I want some I want to put some minimax taste here. So I want some uniformity. So I'm going to assume that mu is in a class of measures that satisfy this in particular for some given constant small r and capital R. And so the result is that if you denote by eta this L infinity distance between the Q's and the Q hats, then you can show that the L infinity distance between the support functions, which are not given by the Q's and the Q hats, but the support functions are going to be at a distance, L infinity distance, that is at most linear in eta, linear in the L infinity distance between the Q's and the Q hats. So maybe, okay, the result is a little more general than that, but basically the result says that if you have two convex sets given by some linear constraints, so by some polyhedral representations, so like here I have the polyhedral representation in terms of the Q's and in terms of the Q hats for G hats. So you need a few conditions. If the Q's are continuous, which is ensured by those assumptions, so the Q's, you can show that if you have those assumptions, you can prove that the Q's as a function of U, QU is a continuous function of U. Then a nice thing, a quite interesting thing is that whenever you have n points, if you define the Q hats, so you project those points in any direction U, and you define the function Q hat of U, it's always a continuous function of U, which is maybe not so intuitive to me, but actually it's always a continuous function of U. So if you have two sets whose polyhedral representations are given by continuous functions, here QU and Q hat U, and if just one of those two sets satisfies the property that it contains a small ball and it is included in a larger ball, then you have that the distance, well, the L infinity distance between the support functions is bounded by constant times the L infinity distance between the two functions Q and Q hat, which is very helpful here, because it means that we just need to control the distance between the quantiles and the empirical quantiles. And then you get such a result. So you get that, I think, something quite surprising. You get that with respect to the Hausdorff distance, the Tukey depth level sets concentrate, the empirical ones concentrate about the population ones, but at a speed that has a rate in terms of n that does not depend on d, on the dimension. It concentrates at the speed 1/√n. So of course, C1, C2, and C3, they're explicit. They all depend. I don't want to give them to you because they're ugly, but they all depend on epsilon. So you remember epsilon, that was from here, the epsilon, the capital L, the small r, the capital R, and d. So the dependency in d is not good. I'm not saying that it's good, but what's surprising is that the dependency in d does not appear in the rate. The rate is really 1/√n. So in particular, you could, using Fubini type arguments, you can prove moment inequalities. For example, the expected distance between G hat and G is of order of 1/√n. And from that, you can even show that the distance between G hat and G is big OP of 1/√n. You can, there are plenty of consequences, but this is the core result.
But that is, I mean, but is it still could be terrible indeed.
It still could be actually no. It could not be terrible. It is terrible. No, unfortunately, there is no magic. There is this surprising thing here, but there is no magic. Okay, and just to convince you that my assumptions are not so bad, for example, any log concave distribution satisfies all the assumptions that I gave you. Okay, any log concave distribution that is not degenerate. If it's degenerate, you just restrict yourself to the subspace where it actually lives.
Can you get nicer expressions for your little r, capital R, epsilon L.
Oh, I wish, but that is actually a very hard problem. If you want to understand small r and capital R for any log concave distribution in terms, for example, of the covariance matrix, imagine you have a log concave distribution with identity covariance matrix. Then you would like to understand those small r and capital R. Let's say that you take A to be the centroid of that distribution. Then I think this would be related to these kind of hyperplane conjectures, and I have no idea of what small r and capital R would be. They would maybe depend on the dimension as well. So any distribution with continuous and positive density that has a decay that is fast enough, and by fast enough I mean at least of order, at least polynomially with degree d-1, then this will satisfy all the assumptions. And also any function that is, any probability distribution that is supported on a convex and compact sets with a continuous density will satisfy all those properties. Compact convex sets also that is not flat. Otherwise, again, you restrict yourself to linear subspace. Okay, so now what about computations? Because all this is nice, but pretty useless, right? I mean, okay, maybe if I talk to statisticians, if I talk to statisticians, well, okay, from experience, I know that if I talk to statisticians in France, they will hear, and they will all clap. Bravo, bravo, bravo. But if I talk, so my experience, I've been to ENSAE, I've been to MIT. If I talk about that at MIT, already 10 minutes ago, many people would have left and said that's useless because computation works. So that is to say that I'm happy that you're still here, so I guess that there are many Europeans here. Or Europeans or Australians or okay, let's look at the computational part of this. So when you look at the convex hull, so remember the convex hull is the zero hull, then there is this quick hull algorithm that computes the convex hull of n points in dimension d in a number of steps that is roughly n to the d over 2. It's n to the integer part of d over 2, which is very bad. It's exponentially large in the dimension. So when you have 100 points in dimension 10, that's really pretty bad. And that is optimal, by the way. There is, if you want, okay, by the way, maybe I should be more precise. What does it mean to compute the convex hull of some points? There are many ways of computing the convex hulls. Here I'm talking about giving the list of vertices. So among those n points, giving the list of which points are vertices of the convex hull. And this takes, for the best algorithm, will take n to the d over 2 steps to compute this. Of course, you could say that maybe this is not very, maybe this is not how I want to compute the convex hull. Maybe I want to give a polyhedral representation of the convex hull. Meaning I want to compute the faces of the convex hull. In that case, there are some algorithms, but the complexity actually depends on the output. So the complexity depends on the actual number of faces of the convex hull that you're computing. But in all cases, it's very bad in the dimension, in terms of the dimension, in general. So now if you want to compute the k-hulls, so in dimension 2, it is known that you can compute the k-hulls. And again, as well, as I told Richard a little earlier, this is not based on the computation of the zero hull and then improvements, local improvements. It's not based on that. So there are a few papers that deal with the computation of the one hull, two hull, etc. in dimension 2 and in a number of steps that is of order n squared. But indeed, when the dimension is greater or equal to 3, there is nothing to compute the k-hulls.
Is it NP hard?
Oh, I don't know if it's if this is known. So an idea would be to approximate the k-hulls, to compute some approximation. So here what I do is that in my case, how do I define an approximation? So you remember that the k-hull, the true k-hull, so the exact k-hull, the exact empirical contour, I'm saying that I said in my previous result that it concentrates at the speed 1 over square root of n. So I'm okay having an epsilon approximation of this k-hole as long as epsilon is not of larger order than 1 over square root of n. Because 1 over square root of n is already my statistical error. So I'm okay having an approximation error of the same order at most. So if I want to do that, that's the basic idea. You remember g hat is given by these linear constraints, and you have infinitely many linear constraints. Of course, the main challenge would be to know exactly which ones are relevant, because you remember I told you that g hat is a polytope. So only a few of those constraints actually matter. But which ones? That's the main problem. And this is what nobody knows how to compute which ones. So what I suggest is, well, what everyone would have suggested after thinking for 5 seconds or 2 minutes, is to just sample random directions, uniformly at random, many of them, and we'll see how many I need. So at least many of them, and look at this approximation. And then okay, a computational cost would be if then, what does it mean to compute this convex set? To compute this convex set, for example, means to compute an oracle, a membership oracle. So if I give you a new point, x, in the space, and I'm asking you, is it in this set? You just need to check m constraints, right? And the computational cost for a membership oracle will be of order n, the number of samples that you have, times capital M. But okay, unfortunately, capital M will be extremely large. Capital M, it will be basically of order n to the d. N to the d, which means that you will, so n to the d minus 1, which means that the computational cost of the membership oracle will be of order of n to the d. And remember, for the convex hole, it was n to the d over 2n that was optimal. So here, okay, I have something very bad. It's much worse than for the 0 hole, but at least it's something. In dimension, if the dimension is not too large, like even in dimension 3, 4, 5, it's maybe not so bad. And the only problem is that this set, this approximation, still concentrates at the speed 1 over square root of n. But now, I need, so in order to get this concentration, I need the same assumptions as before. And also, I was not able to get rid of this, the assumption that QU is subadditive. I need that. So it doesn't simplify the problem so much, because remember, QU is subadditive, so that will just tell me that the support function of G is given by those QUs. But QU hat is still not subadditive. QU hat, when you have an empirical distribution, the empirical quantiles as a function of the direction U, they are not subadditive. So the problem is still complicated. But still, I was not able to remove this subadditivity of QU. So I need QU to be subadditive. And the problem is that I don't know which distributions, except for very simple ones, like, for example, when the level sets are ellipsoids. I know how to do this, but otherwise, I don't know. So, okay. I think that ends the talk. So the conclusion, okay, I think it's pretty clear. So great work. Okay, you know, and yeah, and thank you. And that is based on this paper that you finally accepted after 3 years of fighting. Thank you very much.
Instead of choosing uniform directions on the sphere, you did some kind of sampling from the points that you have.
Yes.
Is that any better?
I don't know. It should be it should definitely be better, but it's much harder to analyze. But it will definitely be better. Yes.
And for some applications, it may be enough to decide for a given point whether it's within the convex set or not. So is that computationally faster? Is it possible to do that faster?
For that, you can actually, there are algorithms. If I give you 1 point, so to get a membership oracle, actually it's known for the exact set, because you just need to check whether the depth is greater or equal to alpha. So this is possible. There are algorithms. I think they are still very bad in terms of the dimension.
So this is naive, but so if I think of the zero hull and I'm estimating the support, I know in some sense the support has to be, it's an underestimate.
Yes.
The support has to be bigger.
Yes.
What happens when I get to 1 null and 2 null? Is it always biased in that way?
So you mean when you want to when you look at for example, the empirical Tukey depth and the Tukey depth itself?
Yeah.
No, it's not biased in the same way, because the empirical quantiles are not always smaller than the population quantiles, or always greater. So they can be in some directions they will be smaller, in some directions they will be greater. But you have to think of so the zero hull, which is the Tukey depth. It's exactly what I was describing for alpha equal 1/n. Imagine that you have x1, x2, xn that are uniformly distributed in some convex set G, and you want to estimate G. So what you can say is that if you take the convex hull of your points, this is the empirical Tukey depth with associated with level alpha equal 1/n, which is outside of my framework, but it's alpha 1/n. But if you wanted to put it in my framework, you would have to say that this concentrates not around G, but around the population Tukey depth contour of order 1/n, which is not underestimated by G hat. But the support itself is underestimated by the population level sets itself. And just to finish, what's surprising is that if you take alpha that is small, like 1/n, then the concentration that I have here, which for alpha that is fixed and strictly between 0 and 1, the concentration is at a speed 1/√n. But if you take alpha, if you allow alpha to approach 0, to be very close to 0 as a function of n, this will become n to the, well, basically if you take alpha to be 1/n, this will be n to the negative 2/d plus 1 in general. In general for uniform distributions on convex bodies. So it will be deteriorated.
So in your problem, you are always assuming a set of points are given. You don't have any freedom to query.
No. It's really offline. Everything is given from the beginning.
Because if one can query, then there is perhaps other results that allow you to do a random
Yeah,
walk,
imagine
for
actually.
example, and efficient.
I don't know.
I mean, there is these things based on random walks, for example, who are computationally very efficient, and you can, if you can ask for an example from the distribution, you can actually find the support of that distribution or various quantities of it.
Yes.
Like very like time linear in M.
For the computation. At least.
Yeah.
So
So computation becomes
Yes,
linear,
yes,
but then
yes.
you have to have some access to your distribution.
Yes.
Take the samples in a careful way.
Yeah, I have never seen any results for this in even in support estimation. I think in support estimation or in the Tukey depth level sets estimation, I haven't seen any
Even
online
Oh,
work.
maybe I'll ask you a little more and see
Yes.
about some recent work people.
Okay. Yes.
So what's the intuition you can remember dependence on D in this
The dependence in D, I get rid of it just because it's the concentration part really comes from the fact that
projection?
Sorry.
Just from the one-dimensional projection.
So one-dimensional projections, which means that here you look at some concentration of some empirical process indexed by a class of hyperplanes or half spaces that has some given VC dimension. So this is really the reason here.
So there's no unibound tag comes in play, even though you go through so many half planes.
Yeah, no, indeed, no. The collection of half spaces actually is parametric. So I think this is one.
Distribution is an act.